Okay, welcome everybody. So in this video, we are going to continue our work with inner products and in particular, taking a look at why identifying whether or not two vectors are orthogonal perpendicular to each other is particularly nice. So to backtrack about why you may want to find what are called orthogonal projections, well, in physics, we generally represent forces as vectors, and we can use the F to denote a force vector. So these forces have a magnitude and they have a certain direction. And we can also express the path that an object is moving with a vector, a velocity vector v. So again, these direction of motion, right? We have a direction that we're moving and we have a speed that we're moving. So velocity is also a vector. And we often will want to decompose this force vector into two components. One component which is perpendicular to the direction that we're moving, and a second component which is parallel to that direction. And what that would look like is, let's say we have our velocities given by this vector in red. So for example, maybe this is like a sailboat that's moving in this direction. And then we have some force, right, acting on this object. So here we can think about the force being wind. So the wind's blowing in this direction and the boat is moving in this direction. And a very common thing in physics to ask yourself would be, well, what component of the force is helping this object move along this path? And that's going to be this component of the force which is moving in the same direction as our path v. So this F parallel vector is written in blue. It is parallel to the vector v. And perpendicular is this vector in green that I've drawn. So this is the component of the force which is having no effect on this object. So when the force is orthogonal to the object, it is not affecting it. So therefore, we can take this wind and decompose it into a component which is affecting our motion plus some component which has no effect on our velocity. This idea of an orthogonal projection is also really important in data science. And so let me explain what's going on in this figure in the lower right side of this slide. That is, let's say we have an observed value of some response variable, y, and we want to fit a model that's going to make some predictions of, given some values of x, how can we predict what the value of y is going to be? And so the prediction for that value we typically denote with a hat on top. So we denote that with a y hat. And the distance of the observed value to the predicted value, these are what we call the residuals or the error of our model. And so in data science, oftentimes what we want to do is we want to fit a model that's going to minimize the sum of all of our error terms. And so this has a really nice linear algebra picture in that we can think about why the observed value as being a vector, and we can think about the fitted value as being the projection of this vector y onto the direction of y hat. And the error of this prediction, well, that would be the perpendicular component of y to this vector y hat. So if you're taking any courses in data science or regression, you're likely to run into orthogonal projections in that context, namely when we have a bunch of observed data and we're trying to predict the value of some response variable, we would like to minimize the error in our model, and orthogonal projections have a really central role in that process. So more generally speaking, given some non-zero vector u in Rn, there are many occasions where we wish to decompose that vector y into a sum of two vectors, one of which is parallel to the vector u, and the other is perpendicular, is orthogonal to that vector u. So let's consider this picture that we were looking at, say, like in the context of data science. So if u is some vector that sits in this plane, then I can take this observed value y and decompose it into a portion which is parallel to vector u, and that's what we're calling y hat. So this is like the parallel part of y, and then we can also have a part which is perpendicular to vector u, and that's the error that we're calling z. So we can write this sum, well, this vector y hat, it is going to be some scalar multiple of u, right? Because it has to be parallel to the vector u. And then we have this other vector which is perpendicular to u that we'll call z. So this vector c times u, we call this the projection of y onto the vector u. So that is this vector right here that I'm drawing in green, is this projection of u onto y. And then we have this second vector over here, which is what we're calling y perpendicular, since that is perpendicular to the vector u. And so we can express y then as a sum of two vectors. The projection of y onto u, that's the component of y, which is parallel to vector u, plus this error term, which is this vector right here, which is perpendicular to u, and that vector is equal to y minus y hat. In the context of data science, this is saying the observed value minus the predicted value, so this is actually telling us the error in our prediction.